Hi everyone, thank you all for watching this talk. So I'm going to talk about Rich 2-to-1 games. This is joint work with Mark Braverman and Subhash Khot. So before we talk about what Rich 2-to-1 games, let me give you some background about what this talk is all about. And so the starting point of this talk is the PCP theorem. And in order to state that, let me first introduce the label cover problem. So an instance of the label cover problem consists of a bipartite graph G and two alphabets sigma L and sigma R, one for each side, each of them being finite, and finally a constraint for each one of the edges of the graph. And a constraint is simply a collection of pairs of alphabet symbols that are considered satisfying. And the goal in label cover is to assign vertices from L, symbols from sigma L, and vertices from R, symbols from sigma R, so as to satisfy as many of the constraints as possible. So there are many problems that can be written in the language of label cover. For example, maxcat, max2sat, tooling, and the list is long. Good. So what do we know about label cover? Well, using label cover, we can phrase the PCP theorem. This theorem says that there exists delta less than 1, strictly less than 1, such that if I give you a label cover instance psi, and I tell you that either you can satisfy all of its constraints, or you can satisfy at most delta fraction of its constraints, then it's NP hard for you to distinguish between these two cases. It's NP hard for you to tell which one of these cases holds. Well, that's a very nice theorem, but if you want to prove hardness of approximation results, oftentimes you need something much stronger than this theorem. So what can you strengthen? Well, there are two obvious things that you can try to improve. First of all, you can try to improve the soundness. Namely, instead of just saying that delta is strictly smaller than 1, you can hope to say that delta is maybe even close to 0. And indeed, such statements are known, and you can either achieve them by what is called parallel repetition, or directly by using subconstant error PCPs. So this talk is not about this type of improvements, but rather another type of improvement, which asks for a better structure from the constraints. So note that in label cover, the structure of the constraints could be arbitrary. We didn't really say anything, just some relation between sigma L and sigma R. So you can hope to make it more restrictive, and hopefully it can be useful. Good. So what is the best structure that one can hope for? So this is this work. So what is the best structure that one can hope for? So this is what I call the ultimate structure. This is what is known as unigames. So what are unigames? Well, a unigame is a label cover instance that satisfies more properties. More precisely, the two alphabets are the same, and each one of the constraints is a one-to-one map. For example, maybe the alphabet sigma L is just a field, and then the constraints could be, for example, linear equations in two variables. Say a minus b equals 1. Good. So this is a very strict structure, right? This is the best you can hope for. And we don't know whether these problems are hard, but we believe that they are, or more precisely, Khot conjectured that they are hard. This is the so-called unigames conjecture. It states that for all delta greater than 0, for sufficiently large alphabet, if I give you a unigames instance, it's NP hard for you to tell me whether it's almost fully satisfiable or at most delta satisfiable. So I want to make one remark here. Note that here, instead of the one that we had in label cover, we had here 1 minus delta. And this is inevitable because if you have a unique game that is satisfiable, then it's easy to solve it. So this is really the best you can hope for. So this is the reason this conjecture is stated this way. Well, okay, so this is the best structure we can hope for. So why should you study it? One reason is that if you are able to prove that this problem is NP-hard, then in route you would prove that many other problems are NP-hard. Namely, once you assume unique games, you can show hardness approximation results for many problems. Oftentimes they are tight. For example, for vertex cover, max cut, and for general CSPs. So this is certainly one pro of the conjecture. But of course, this is a conjecture, so by definition, this is a con. It's a conjecture. We don't know if it's true or not, so we hope that it's true, but we don't know how to prove it. Okay, so let's maybe relax our structural requirement. Let's maybe settle for something a bit less restrictive than one-to-one in the hope that maybe we can prove it. So what is the least restrictive, the most restrictive structure that is not one-to-one? Well, this is what is called two-to-one games. Again, a two-to-one game is simply a specific type of label cover in which the alphabet sigma L is twice as large as sigma R, and each one of the constraints is a 2-to-1 map. For example, maybe sigma L is a field, sigma R consists of all the quadratic residues, and each constraint is a quadratic equation, such as a squared is equal to b. So this is one example of a 2-to-1 game. So for this problem, in the same paper, Khot also conjectured that this problem is hard, but now you don't need this 1 minus delta anymore. He simply conjectured that for all delta greater than 0, for sufficiently large alphabet, given a 2-to-1 games instance, it's NPR to tell whether it is satisfiable or at most delta satisfiable. Well, so we cannot prove the conjecture as stated, but we can prove something very close to it. So this is the 2-to-1 games theorem. So it's stated for every epsilon, for every delta greater than 0, for sufficiently large alphabet, it's NPR to distinguish between almost satisfiable 2-to-1 games instances and at most delta satisfiable 2-to-1 games instances. So this is good because this is a pro. It's provable. It's a very restrictive type of structure, so we're happy. But somehow, unfortunately, this difference between 2-to-1 and 1-to-1 really seems to make a lot of difference as far as applications are concerned. So there are less applications, there are some, but there are certainly less, and oftentimes this type of theorem is not enough to prove tight inapproximability results. So the main question that we ask ourselves in this work is, are there any intermediate problems between 2-to-1 games and unique games? So I'll show it shortly. The answer is yes, and we're going to spend the next couple of slides in order to define these problems. Okay, so now we are going to define a new parameter for problems, which is called richness, and this is what will define our intermediate problems. So recall that a 2-to-1 game is simply a label cover instance where each constraint is a 2-to-1 map. Now we're going to define partitions. So what do I mean by that? Well, let's fix some vertex u on the left side. And let's consider each one of the neighbors of u. So I claim that each neighbor v of u defines a partition of sigma L into sets of size 2. And why is that? Well, look at all alphabet elements of sigma R and look at all the preimages of them according to the 2-to-1 map between U and V. So for each sigma, there are 2 preimages. So this collection of preimages is a partition of sigma L into sets of size 2. Okay, so this is simply the partition that U and V define. And now that we defined this partition, we can look at the distribution of the partitions that is associated with U. So what do I mean by that? Well, for each vertex U, consider the distribution of the partitions PUV, where you sample V uniformly among the neighbors of U. And the richness parameter that we'll care about sort of measures how random looking this partition looks like among all partitions of sigma L into sets of size 2. Okay, so this is the rough intuition, but now let's make it a bit more precise. So here is the definition. For an integer R and a 2-to-1 game, we say that the 2-to-1 game is R-wise rich if for each vertex U on the left, if you look at this distribution of the partitions that is associated with it, this distribution is R-wise independent. In the sense that if I tell you R-1 pairs in it, the R pair would still look uniform. And in case R is the maximum that it can be, in case R is the size of the alphabet of the right side, we say that the game is fully rich. And often we'll just omit the fully and just say that it is rich. Good, so this is the main definition that we'll care about. And now that we have that, I can tell you our conjectures, which are new conjectures that sort of make a way between 2-to-1 games and unique games. So our first conjecture is asserts that rich 2-to-1 games remain hard with imperfect completeness. Namely, for every epsilon greater than 0, for sufficiently large alphabet, if I give you a fully rich 2-to-1 game, it's NP for you to tell me whether it's almost satisfiable or it is at most epsilon satisfiable. But note that now that we're looking at 2-to-1 games, there is no reason to believe that satisfiable instances are easy anymore, unlike unique games. So it makes sense to consider an even stronger conjecture, which I call here conjecture 2, which asserts that for every epsilon greater than 0, for sufficiently large alphabet, if I give you a fully rich 2-to-1 game, it's NPR for you to tell me whether it's fully satisfiable or at most epsilon satisfiable. Great. So now that we have presented these two conjectures, there are several questions that come to mind. Here are 2 of them. First of all, how do these conjectures relate to the unique games conjecture? Are they weaker than it? Are they stronger than it? Maybe equivalent? Maybe incomparable? So that's one question. And the second question is, okay, so why would you study these problems? What is good in them? And I hope that I'll convince you that these problems are interesting. So here is our main result. Our main result asserts that conjecture 1 is in fact equivalent to the unique games conjecture. That is, UGC holds if and only if conjecture 1 holds. So let's take a moment to make some corollaries. So it means that if you look at R-rich 2-to-1 games, where R is not full, then these problems are intermediate problems between UGC and between 2-to-1 games. So you can think about it as sort of a ladder between 2-to-1 games and unique games, and the higher in the ladder you go, the closer you get to unique games. So it makes sense that in order to make further progress on UGC, we'd have to develop some tools that show hardness for rich games. But from a different perspective, another way to look at this theorem is as saying that conjecture 2, namely the conjecture with perfect completeness, is in fact strictly stronger than UGC. And this is very interesting because one feature of unique games, which is very limiting, is that it has an imperfect completeness. And therefore, we cannot apply it all the time. For example, if we want to prove hardness for coloring problems. But conjecture 2 doesn't suffer from this lack of perfect completeness, so we can hope to use that. So I'm not going to say too many words about the proof. I'm going to show you sort of the main lemma in the next slide. But I do want to say that the point of this theorem is not really the reduction. The reduction is fairly standard. It is the reduction from the paper of Khot, Kindler, Mosel, and O'Donnell. And the real novelty here is in the soundness analysis. So many times in PCP reductions, you have to use some sort of analytical machinery. Sometimes it is in the form of the hypercontractive inequality. Sometimes it's the invariance principle, but really always you have to use something. And in our work, we do use some analytical tool, but we use something a bit exotic. Namely, we're using a hypercontractive inequality on the symmetric group, which was just recently established. So how does this enter the picture? Well, I don't have time to tell you the whole proof, but here is the main lemma. So to tell you the main lemma, I need to make one quick definition. So suppose I have a bounded function f from 0, 1 to the 2n to 0, 1, and I have some coordinate. Then the influence of coordinate I on f is the expected square difference where you sample x uniformly from the cube and you look at the difference between f of x and f of the point that is x, except that it's different in the ith coordinate. Good, so now one more definition. So if I have a function from 0, 1 to the 2n to 0, 1, and I have some 2-to-1 map pi from 2n to n, then I can define the projection of f along pi. The projection of f along pi is a function that takes n bits and outputs some number between 0 and 1, and it's simply defined as f at point x, it is simply defined as f of y, where y is the pre-image of x. Namely, for each coordinate, yi is equal to x at a coordinate pi of I. Good. So now that we have the definition of inferences and projection, we can state our main lemma. And there are several parameters in it, but really the idea here is that if you have a function that has low degree and has all of its influences being small, and you take a random projection of it, then the function will still have small influences. More precisely, for all tau greater than 0 and d, there exists some tau prime, such that if you have a function of degree at most d, all of its influences are at most tau prime, then if you choose a projection pi uniformly, with high probability, the maximal influence of the projected function will be smaller than tau. So this is the main lemma. I think that it's interesting kind of by its own because it's a kind of a natural analytical question. And if you're a bit familiar with PCB reductions, you can maybe imagine how it enters the picture, but otherwise, I agree that it's a bit unclear, but trust me, this is the main thing that you have to do. Yeah, and as I said, in order to prove this lemma, what you really need to do is do some analysis on the symmetric group Sn. Good. So let me finish the talk by some discussion and open problems. So first of all, we look at the notion of R-rich 2-to-1 games. And though I didn't say that, if you look at R equals 1, this is exactly the same as the 2-to-1 games instances that we currently know that are hard. And we know that this type of instances imply that unique games is hard between half and epsilon. Our main theorem in this work is to say that if you have full richness, then you get the whole thing about unique games. You get unique games between 1 minus epsilon and epsilon. And an interesting question here is, what do you get from R richness with R that is more than 1, say 2 or 3 or 100? Would you get any improvement over unique games between half and epsilon? So I think that this is an interesting question. It would be good to know. The second question is, what can we do with conjecture 2? What can we do with hardness of 2-to-1 games with perfect completeness? So can we use rich 2-to-1 games with perfect completeness in order to establish hardness results for satisfiable instances, say for CSPs? So this is something that I think that is possible and is promising. And in fact, currently we have a work in progress that does some preliminary steps along this direction, together with Braverman, Khot, and Lifshitz. And finally, in a maybe more abstract sense, so we know that in order to prove hardness for 2-to-1 games or for R equals 1, what you really use is the so-called Grassmann graph. So this is the main object that you need to study there. And it's interesting to ask whether there is some combinatorial gadget that would plausibly imply hardness of R-rich game with R greater than 1. So even if it's only a candidate, it would be very interesting to know. And I think that if we come up with something like that, then it will lead to further progress on all of this direction. So I hope that you enjoy this talk, and thank you very much.